Okay, let us continue with the Jesus. Let us continue with the second part. Thank you. Let us continue with the second part of the third day of our symposium of the International Society for the Philosophy of Chemistry. Can you hear me well, Vanessa?
I can. Can you hear me?
Yes, actually we can. So I would like to introduce Vanessa Seifert with her lecture, The Many Laws in the Periodic Table. So unfortunately, I can just tell you when you have 5 minutes left, interrupting you. So I'm sorry for that, but you can start right now.
Can you see the slides? Can you see me?
Yes, we can. Exactly. Everything is working perfect here. So
okay.
Yes, we can see the slides.
Perfect. Okay, so I can only see the slides. I cannot see anything else. So just interrupt me when it's time. Thank you and for having me. Thank you to Olympia, to Juan Camilo and everyone in Argentina for setting up this hybrid ISPC event. So us who cannot come can actually attend and take part. So I'm very grateful for that. So today I'm going to talk about, I'm going to be quick because the time is not a lot for all the things I want to say. The argument, the claim I want to convince you about is that there are many laws in the periodic table. I will try and give you arguments in favor of that. And of course, I'm going to try and explain what that claim exactly states. Before starting, I should say also that I'm very happy. I'm extra happy today because this is the first event I take part in as a Marie Curie Fellow, which my project called Chemical Reactions as Causes and Laws started this month, this July, and this is the first deliverable that I'm proud to realize in the context of this project. And of course, it also has to do with laws. Eventually, more stuff hopefully will be produced. Now, the thing I'm going to present today has been mostly the result of what I've been working on at the University of Athens under another project called Nomos with Stathis Psilos. Of course, all these are interconnected because it is within the context of metaphysics of science. So I'm going to stop saying about all this and let's go into philosophy. So first, the plan today: motivate the talk, spell out the claim, namely that there are many laws in the periodic table, offer support to that claim by 3 main arguments, and then discuss 2 main challenges, hopefully I'll have time to do that, against the claim that there are many laws in the periodic table. So let's go to the motivation first. Why think of the periodic table in terms of laws of nature? So here I'm not going to talk a lot about motivation here, primarily because this is an audience that already knows a lot, and I'm sure more than I do, about the periodic table. But let me just pass through this quickly. So we have this periodic table, a visual classification of all known chemical elements. They are classified in terms of increasing atomic number, the modern one, but also the elements are grouped into sets, different kinds of sets, the so-called groups, periods, and families. Now, chemists use the periodic table in order to make inferences and to express statements about the chemical and physical properties of matter. So they talk about they explain the boiling and melting points of matter in terms of the position of the elements that constitute said matter. They explain the reactivity, electrical conductivity, density, and so forth in terms of the position of elements in the periodic table. So, for example, they would say that matter consisting of elements that belong in the set of alkali metals exhibit are highly reactive, and exhibit low melting and boiling points. Or matter that consists of elements that belong in the set of metalloids are shiny and malleable, right? Also, they make inferences and express statements about chemical transformations. So they would say that matter that is made of elements that belong in the set of alkali metals react with water under standard conditions, or earth metals react with acids and so forth. They also make statements about periodic trends. So for example, they would say that, elements that are found further up and right exhibit non-metallic character, or further down and left have a, increasing atomic, have a smaller atomic radius and so forth. So we already have here, what I want to insinuate here is that chemists use a periodic table in order to formulate statements that help them explain the physical and chemical properties of matter. That's what I want you to keep essentially from all this. Now, where does the term law come in? Actually, even though the term law plays a very important role in philosophy and metaphysics, it's a separate tradition there, the term has also had a very long tradition in the history of chemistry. And in fact, mention of the term periodic law starts with the beginning of initial formulations of different classifications of chemical elements. So for example, Newlands talks about the so-called law of octaves. He says, I claim to have been the first to publish a list of elements in order of their atomic weight, and also the first to describe the periodic law. See, we already have a first mention here. Of course, obviously, Mendeleev, another important figure who also talks about the periodic law, he names his paper periodic law as well. He says, I define the law of periodicity as the mutual relations between the properties of the elements and their atomic weights, which can be applied to all the elements. How the periodic law is defined historically is not of concern at the moment. What I want you to keep from this is that the term law has already been in use with respect to the periodic table for a very long time. And it's still in use in contemporary chemistry. I know my references might not be so prestigious, academically prestigious, I suppose, but nevertheless. So Wikipedia, for example, says that a graphic formulation of the periodic law states that the properties of chemical elements exhibit an approximate periodic dependence on their atomic numbers, or the Oxford Dictionary defines the law as the principle that the physical and chemical properties of elements are a periodic function of the proper proton number. So we already discussed the periodic table by using the term law. And this is interesting because even though it seems that the term law is not used in a particularly philosophically nuanced manner, it does, from a philosophical perspective, prompt you to think whether actually you can think of the periodic table as a law in such a way. And of course, and this hasn't been done so far. In fact, there haven't been lots of chemical case studies that have been considered from this perspective of lawhood. Now, what I mean by perspective of lawhood is essentially I'm referring to the whole tradition that has been developed independently in philosophy of science and metaphysics about laws of nature, right? Of course, an exception is the laws of thermodynamics, if we consider thermodynamics as being part of chemistry. Now, with respect to the periodic table, there has been only one or two, I would say, Weisberg and Hettemann, if I'm not wrong, who have discussed in some way or another about the periodic table as some form of law or theory, Weisberg calls it, which philosophers would say, some philosophers would claim a theory is just a set of laws or law-like statements, I suppose. But in general, the received view in philosophy of chemistry is that the periodic table is just a classification, right? It's a heuristic representation and doesn't particularly have a metaphysical weight. Now, I don't want to say that philosophers of chemistry have explicitly denied this claim, but so far it has been handled primarily as a heuristic tool and hasn't been considered from a robust metaphysical perspective. And so this is an attempt to do so in this talk, essentially. So what is the claim? The claim is that the periodic table embeds many laws of nature. And what do I mean by that? I mean that there are many regularity relations that are identified within the table and which constitute as good candidate laws as other paradigmatic laws of nature that have been considered in philosophy. So as good a law as one would regard Newton's laws of gravity, laws in optics, Maxwell's equations, and so forth, right? So here, this is a tricky point that I need to clarify. I am not explicitly, the claim is modest in the sense that what I want to say is that the regularity relations embedded in the table are just as good candidates as other candidates of laws, should we admit the latter as such, right? Now, for example, such regularity relations are actinium reacts rapidly with oxygen, halogens undergo redox reactions, lanthanum reacts with the halogens at room temperature. Now, the claim is twofold. The first is that the periodic table represents non-accidental regularities. That's what I mean by lawful regularities or candidates of lawful regularities. And the second claim is that it is not a single regularity relation that I'm trying to defend here as being a good candidate of a law, but many. So essentially what I want to claim is that the table is a depiction of regularities, of many regularities, about specific chemical and physical properties of specific elements or sets of elements, including of groups, periods, and families. And all these regularity relations are candidate laws of nature. Now, obviously, this is not the standard, this doesn't match the standard understanding of the periodic law. I'm not defending that what is a law here is what Mendeleev or even Wikipedia defines as a periodic law. Instead, it is a set of statements that chemists produce by studying the periodic table. Now, what do I mean by when I say that table represents laws of nature, or identifies laws of nature, or that non-accidental regularity relations are expressed by such statements is, so here these terms should be taken to an extent naively. What I want to confer is just the idea that chemists employ the table as a means to visually depict and examine regularity relations between elements. Now, I've had pushback, and that's why I'm stressing this. What I do not claim that the periodic table is a law of nature. I claim that the statements that chemists express by studying the classification of elements through the visual depiction of the periodic table correspond to good candidate laws of nature. Now, how to support this claim? First, sorry, I'm shouting. First is those regularity relations that are embedded in the periodic table seem to satisfy equally well those features that are standardly associated with other paradigmatic examples of regularity relations. Now, of course, here I should say that in the literature about laws of nature, there is extensive disagreement about which features are actually appropriate features of lawhood, which ones are necessary and sufficient in order to infer that a regularity relation is non-accidental. I'm not going into this discussion. I'm just going to show you that some of the main features that crop up usually in the literature as standard features of laws apply and are satisfied by the regularity relations here as well. So the first one feature of lawful regularities is that the corresponding statements are factually and not logically true, and that they do not involve proper names, but general concepts. So for example, if I'd say, Vanessa drinks orange juice every morning, this is not a lawful regularity because it talks about the specific person, which is Vanessa in this instance, right? Whereas if I say that oxygen reacts with hydrogen to produce water, this doesn't involve proper names and therefore satisfies this feature of a lawful regularity, right? Also, these statements are not logically true. You discover them by empirically examining nature, essentially, in order to decide whether they are true or false. So, for example, gold is shiny, the validity. No, I'm going to go through that. I already explained it. Second feature now. A second feature of law-like statements is that they can be used to make successful inferences about particular instances of matter. So, for example, do I have an example here? No. So if I say, for example, gold is unreactive, this law-like regularity can be used in order to infer that my golden necklace will never rust, that the gold that someone discovers in a mine in Africa will never rust either, and so forth, right? So specific instances of specific instances of matter that are satisfied by those general statements can be explained, and one can infer about their behavior by those statements of laws.
5 minutes, Vanessa.
5 minutes already? I see. Okay. The other three features is that these law-like statements unify the behavior of disparate things, they systematize empirical facts, and they correspond to universal or statistical claims. So essentially the point is here that statements like these hold at every time and place in the universe and for all relevant instances of matter. So whether I talk about how oxygen behaves, how oxygen reacts with hydrogen, this will apply to the oxygen outside my house, even if I find it in Mars, or about the oxygen 100 million years ago, right? Now I'm going to move. Two features that are the most problematic perhaps, but that are standard features of lawhood, is that they allow predictions and that they explain phenomena. And now these are the two ones that need to be resolved in terms of how we reply to these with respect to the periodic table. But in general, it seems that prima facie, when we talk about statements embedded in the table, such as gold is shiny, this allows us to make prediction about any kind of gold we will encounter in the future, but also explain instances of matter where we find gold and it's seen to be shiny, right? Now, I'm going to try and offer the second argument as well. And the second argument to think of these law-like regularities as good candidates of laws is that they can be spelled out in terms of the two main candidates of laws of nature, namely the regularity and the necessitarian view of laws. So in terms, for example, of the best system account formulated by Lewis, who says that laws of nature are just regularities expressed by the axioms and theorems of an ideal deductive system, you could indeed say that this account applies coherently in the case of the statements of the periodic table. So, for example, one could take that the principle of distinguishing elements in terms of atomic number is an axiom of the system, and the regularity relations which come out of that ordering, in part out of that ordering, are the theorems of that best deductive system. So essentially here, my point is that if we think of those regularity relations in terms of standard accounts in metaphysics of laws, we can coherently do so. And this is a good argument for why we can think of them as candidate laws of nature. The same if one is a necessitarian as well. So suppose that we take the statement gold is unreactive. Here, as a necessitarian, I would say, well, this doesn't only reflect a regularity relation between gold and unreactive, but a necessitation relation between being gold and being unreactive, right? So again, here, my point is that one can apply metaphysical views of laws coherently in the case of these regularity relations in the periodic table. Now, I'm going to go over this and go to the two main challenges. So a standard objection, what has been done before with respect to the periodic table, there has been this point made by Eric Scarry and John Worrell in a joint paper that the periodic table is not as good, is not as successful a predictive tool as has been initially thought by philosophers of science. So, for example, Lipton said famously in 1991 about the table that when Mendeleev produced a theory of the periodic table, the community was only mildly impressed. But when he used his theory to predict the existence of two unknown elements that were then independently detective, that's what essentially put the Mendeleev's version of the periodic table as the choice of the right table, right? And this kind of built a tradition, a philosophical tradition called predictiveness, which kind of put a lot of weight to the value of predictiveness when it comes to theory choice, right? And this was challenged in some degree by this paper, where Worrell and Scarry said, well, actually, it wasn't as successful as a predictive tool as philosophers would like to think, because there were also false predictions made by Mendeleev, unsuccessful ones with respect to certain properties, and it's more of a methodological tool, right? So here what we see is an insinuation that we have to think of the table more as a classificatory tool rather than a theory in some sense. Now, a way to respond to this in a sense that saves the claim that the regularity relations are good candidates of law-like regularities is that, first of all, we shouldn't confine those regularities to the examination of the predictive success of Mendeleev's table. But also we shouldn't confine it to how successfully it's used to predict the existence of new elements, right? We have to rather see how the regularity relations that are expressed by the table, by the modern table, are used to make novel predictions by looking at different empirical and theoretical discoveries that are made in various areas of study. And here what I'm thinking about is the use and the value that these regularity relations have in predicting biological phenomena, geological phenomena, paleontological phenomena, but also astrochemical phenomena, right? It's amazing the value and usefulness of those statements embedded in the periodic table and predicting things in the in the future, but also in far back in the past, and far away from Earth, but also right here, right? And I think this is what maintains the predictive success of those relations. I'm sure I'm over time, but I'll try and wrap up. Now, the second, and I think the most and a harder objection, a more problematic objection against my claim, has to do with the explanatory power of those regularity relations. And this has to do with a more general worry if you come from a reductionist perspective. Because a reductionist could claim that, well, you may use those regularity statements produced by the periodic table to explain, the chemical and physical properties of matter, but what ultimately does the explaining is the subatomic particles of which that matter consists of, right? And so those regularities, in virtue of being reduced to more fundamental physical regularities, kind of lose their lawful status. Now, this is a very general and persisting problem in philosophy of science. Kim, for example, famously has talked about this. You know, he says, if there are physical laws, why do we need special science laws? And indeed, this is a problem. There are different solutions, though. The obvious one is to deny reductionism, which is a valid way to go. So by saying that chemistry is not reduced to quantum physics, you can maintain the lawful status of those regularities. But given that I'm not particularly inclined to support anti-reductionism in such a way, another way to go is to maintain reductionism, yet make a distinction between what a law explains and how a law is explained, and maintain, therefore, that, you know, a law might be reduced to more fundamental physical laws, but that doesn't mean that it doesn't have genuine explanatory power. Now, how you can maintain this claim, I cannot go over this, but there are ways that one could support this argument. Now, conclusions. I'm not sure I've convinced you in such a short time, but essentially what I wanted to say today is that there are very good reasons to think of the regularities in the table as candidate laws, or at least as good candidates as other paradigmatic ones. These are not the same as what people call the periodic law. They are much more precise, and there are many, not one. Of course, here, a lot of things have to be figured out. First of all, you have to decide whether you want to view those laws as a necessitarian or as a regularity theorist or something else. But also you have to solve important issues regarding explanatory power and reductionism. That's it. Here are the references. Hopefully soon my book will come out, Chemistry is Metaphysics, where I talk about this in chapter 3, and also a paper which is under review. Thank you very much.
Thank you. So we have 5 minutes for questions, and people is clapping if you can hear them. So we have just 5 minutes of questions. Please be brief if someone wants to ask something. Michelle, yes.
Hello, thank you for the talk. I might have missed some part of what you said, so just clear it up if I did. So I just want to push you on the explanatory power part a little bit further. In the philosophy of explanation sort of literature, a lot of explanations end with a law. Now, if the laws are in the periodic table, you can end your explanation by pointing to the periodic table and saying, look, it's, you know, this element is one of the blue ones, that's why it's shiny, or look at its position in the periodic table, and that's when the explanation ends. And so explaining a law is a very different sort of exercise. So anyway, I just, would you accept that if the laws of nature are in the periodic table, really in the periodic table, then you can end an explanation by pointing to the periodic table?
Yes, so this is why this is a complicated problem. I cannot give you a straight answer because it very much depends on how you understand explanation, right? It seems that you insinuate that the kind of explanation you're going for is kind of a deductive nomological explanation, I suppose, but this is not something that one needs to adhere to, right? And I don't want to block the possibility that, you know, a law like regularity, a statement of the periodic table is in turn explained by laws in physics.
No, you wouldn't necessarily need to, but anyway, I'll let the other people ask questions.
Thank you, Michelle. So does Depanvita, does Gupta?
Yeah, hi. Do you hear me, Dr. Seifert?
Yes, we can.
Yeah. Okay, I really have a one-line question. I've been wondering about your psychological motivation behind the project. Is it because you thought such an, you know, ancient science, central science, so successful in making inferences should have a set of its laws? Is that where the project comes from?
No, No, I wouldn't say that I had such a motivation. I'm trying to be more open-minded in the sense that, you know, if I thought that there are no laws in chemistry, I would want to maintain that. I don't think that it is vital for chemistry or philosophy of chemistry to believe in laws. I was curious about the question in the first place, mostly because working with the group in Athens, the group in Athens is very active in metaphysics and in talking about laws of nature. And so when they asked me once, you know, can you think of a candidate law in chemistry? Automatically, because of my studies in chemistry, I thought periodic law, you know, it's a catchphrase. But then looking at the literature and, you know, looking at the fact that there's not a lot of talk, of serious talk of how the periodic table can be construed in this metaphysically nuanced way, I was just curious of how you could do that. So I viewed more as a puzzle rather than as, how would I say that? As something where I'm really committed to trying to defend that they have lawful status.
Thank you. A short one, Jerry, the last one, please.
Yes, very quickly. Very provocative talk, I must admit. Exciting in that context. One short question is the laws of physics. Generally speaking, most metaphysicians that I'm aware of equate some sense of mathematical logic with the laws of physics, such that they have some sense of intimate relationships between observations and predictions and consequences. So the issue here would be, are you asserting that the table of elements has a formal basis in logic as well as in metaphysics?
No, I haven't thought of that, to be honest. My intuitive answer would be no, but I don't have a good justification for that. But I would resist that metaphysicians think of physical laws in terms of logical connections, to be honest. And I think there is a distinction that we need to make between whether physical laws are represent some sort of logical necessitarian relations, but a very strong necessity there, or whether they reflect metaphysical necessity. I don't think that metaphysical necessity has the same strength as logical necessity. And I think these two need to be distinguished. If it were logical necessity, it would be much harder to defend my view. Just because, you know, it's initially, prima facie, it's not framed in terms of logic, is it?
I guess you're separating logic then from philosophy in general?
It's a really interesting discussion, but unfortunately, we need to go with Elena because we are just in time. So I'm sorry for interrupt both of you. Elena, are you here with us?